Hello everyone, I am Dr. Naresh Kumar, Assistant Professor in the Department of Electrical and Electronics Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to have a discussion on EMF equation derivation in the transformer and its related problems. So first, what is transformer? Transformer is a static device which transfers electrical energy from one circuit to the another circuit. This is one circuit and this is another circuit without any electrical contact. This is magnetic circuit. Magnetic material without any electrical contact, it will transfer electrical energy from one circuit to the another circuit without changing the frequency. Supply frequency and load frequency must be same, and here flux is also same. So these are the terms. So first, if you give the electrical some amount of AC supply, so V1 voltage, that is a primary voltage, and if you give the primary voltage to the winding, so the winding which is connected to the transformer supply is known as the primary winding. So primary winding turns are N1, and next, and this supply voltage is V1. Next, here E1 and E2, that I will explain in the next part. And next, N2 turns, secondary winding turn, the load, if you connect the load, this is the load. This is the load voltage is the secondary voltage, that one. And next, N2 is the secondary winding turns, and E1 is a primary induced EMF, and E2 is a secondary induced EMF, and this is the flux. Flux circulates in the transformer core, and F is the supply frequency. Supply frequency, load and supply is same. Now here, if you give the AC supply to the transformer primary winding and current flows in the transformer winding and it sets up the flux, this flux links with the transformer primary winding, and this flux, as it is a magnetic material, it circulates in the magnet core, and it also linking with the transformer secondary winding, and induced EMF will be developed in the transformer secondary winding according to the Faraday's law and mutual inductance concept. Induced EMF will be developed, and if you connect the load and induced EMF and current flows in the secondary winding, that current is I2, and the terminal voltage is the V2, that is secondary voltage, that is load voltage. These are the terms. V1 is the primary voltage, V1 is the primary voltage, and V2 is the secondary voltage, that is load voltage. This is the supply voltage, and E1 is the primary winding induced EMF, and E2 is the secondary winding induced EMF. And next, N1 and N2 are primary turns and secondary turns. So here N1 having more number of turns as compared to the secondary winding turns. Now it is a step down transformer. If these number of turns more or less, and if these number of turns are more, then that is step up transformer. Next, N1 and N2, primary turns, primary winding turns, and secondary winding turns. N1 and N2, phi is the flux linking, and F is the supply frequency. That supply frequency in hertz. Now, so this is the diagram as we have seen. Now, if here transformer primary winding is given to the supply is given to the transformer primary, and that supply is the sine wave supply. AC supply we are giving, that is AC. So that AC supply is, and when you give the supply voltage to the transformer primary winding, current flows in the primary winding. This I1 current flows in the primary winding, and this current setups the flux. That flux is phi, that is phi of t. So if AC supply, AC voltage is sine wave, this is, and this current is also sine wave, that this magnitude is depending on this impedance, this primary winding impedance, and this current is also set up the flux. That flux is, it looks like this, that one is also AC sine wave. Now here this is the omega t. So this is the flux waveform. When you give the AC supplies, AC sine wave is given to the transformer primary winding. That there is a current, the current flows in the primary winding, that current sets up the flux. That flux waveform, it looks like this. And here, what is the time period here? So this is up to here one cycle. So time taken to complete one cycle is known as the time period. So up to here, this is one cycle. Complete set of positive and negative values is known as cycle. Up to here, one cycle, though, this is the time period. This is 0, pi, 2 pi, 3 pi and 4 pi. This is second cycle. So this time period is also, so this is first cycle and second. First cycle up to t equals to pi. Time period is 2 pi. And here the maximum value of flux, phi maximum, and this one is the negative maximum. So maximum value of flux occurs at pi by 4, and means that is t by 4. Now here, according to the Faraday's law, mutual inductance concept, without any electrical contact, so induced EMF will be developed in the transformer secondary winding and primary winding. So if you give the AC supply to the transformer primary winding, so now here there is a current in the primary winding, that current set up the flux. This flux links with the transformer core. So that is flux, and this flux links with the transformer secondary winding, and induced EMF will be developed in the transformer secondary winding according to the Faraday's law. Now here, this is Faraday's law. E is directly proportional to the d phi by dt. So here, what is d phi by dt? Here this flux. So from the flux waveform, I will derive the EMF equation in the transformer. Now first here flux, change in the flux with respect to the time. What change in the flux? Here flux is changing with respect to the time here. So flux value. So this is the time period t. This is up to here t by 2. This is 3t by 4, and next this is the t by 4. So I am considering these 2 points. So this is 0, 0 time value, and this one is the, this point is the t by 4, 5m. So between these two, so rate of change of flux. So maximum flux, and this is the maximum flux, and here is the flux value is 0, and there is a flux value is 5m, maximum flux. So change in the flux with respect to the time during this period t by 4. So 0 and pi m minus 0 divided by t by 4 minus 0. This one. So 5m minus 0. So if you consider these two only during this period, so t by 4 and 5m minus 0. Now here, so 4 it is in the denominator. So if it is comes to the here 4 5m divided by t. Here what is meant by time period? Reciprocal of frequency. Now what is the formula? So reciprocal of frequency is known as time period t equals to 1 by f. Now if you substitute in this, average EMF per turn E equals to 4 into 5m into 5. So this 1 by 5 t is known as, that is frequency. So frequency means number of cycles completed in a second is known as frequency. Frequency units are hertz. Now here, this is the average EMF. Average EMF is different, and RMS EMF. You can calculate the average EMF and RMS EMF for sinusoidal waveform. Already we discussed about average value, RMS value, form factor and peak factor for different waveforms, for different AC waveforms in the first module. So that I already explained with different types of waveforms. So now here form factor. So form factor for our sinusoidal waveform. So this one is also I explained. So in the next slide I will explain this form factor for sinusoidal waveform. Next slide I will explain this one, 1.11. This one in the next slide I will explain. Don't worry. Now form factor equals to RMS ratio of RMS value to the average value, that equals to, this value is different for different types of waveforms. For triangular wave it is different, for square wave it is different. So for sine wave this value is 1.1. This I will explain in the next slide. Now here this is our average value. So form factor equals to 1.11 for this particular. So from this we can derive the RMS EMF per turn, ERMS equals to, that we can write here ERMS equals to, substitute this, if you RMS value equals to 1.11 into average value. So this is the average value. So RMS by average equals to 1.1 for sinusoidal waveform, sine wave. Now here if you multiply with this 4 into 1.11, 4.44, 5 into En, and in the per turn, this is only for single turn. So for N in the primary winding turn, induced EMF E1 will be developed in the primary winding and secondary winding. So E1 equals to, multiply with N1. So multiply with, this is only for one turn. So if you, for N1 number of turns, so they are connected in series turn number of turns. So multiply with N1. So now RMS EMF in the primary winding E1 equals to 4.44 5M into F into N1. For secondary winding, RMS value, RMS EMF in the secondary winding E2 equals to 4.44 5M F into N2. So only the difference is N1 and N2. Depending on the number of turns in the primary winding and secondary winding, that induced EMF value will change. So if it is N1, that is E1, if it is N2, and that is E2. Now here this explanation is important. So already we discussed for voltage waveform in the RMS value calculation, average value calculation, and form factor calculation. But here I will explain with this flux waveform only. I am changing the term V and phi here. Now this I am deriving form factor for RMS value and average value. So first determine form factor for sine wave. So first calculate the average value. This is a sine wave. So this is the omega t and this is the phi of t, pi, 2 pi and 3 pi and 4 pi. So now it is a symmetrical waveform. Phi of t equals to this one. This phi of t equals to phi m sin omega t. Now here what is the time period? Time period equals to 2 pi. So it is a symmetrical waveform. So consider only off alternation. So F average equals to 1 by T2. Up to here only you calculate 1 by T by 2, 0 to T by 2, F of T dt. For asymmetrical waveform, you consider full cycle. It is a symmetrical waveform. Positive off cycle and negative off cycle is same. F average equals to 1 by T, 0 to T, F of T dt. This is not required. Here it is a symmetrical waveform. Use this formula only. Here time period equals to 2 pi. So up to pi only calculate the average value. Now up to 1 by average value equals to 1 by 2 pi by 2. 2 gets cancelled and 2 pi by 2 gets cancelled. And next phi m sin omega t, V of t. This is the phi of t. So now here if you simplify this one. So now here integration of sin omega t phi m by pi. Sin omega t is the minus cos omega t from the limits are 0 to pi. Now here phi average equals to 2 phi m by pi. This is the phi, 2 phi m by pi for this particular sinusoidal waveform of flux is 2 phi m by pi. Now we for form factor equals to RMS by average. Average we calculated here, and first calculate the RMS value. Next, this is phi m omega t, 0 pi, 2 pi and 3 pi, 4 pi f of phi of t, and this is the omega t. Now here RMS value equals to, for symmetrical and asymmetrical, consider full cycle. Here 1 by t 0 to t f of t square dt. This one here function is the flux phi RMS equals to square root of 1 by 2 pi. Here 2 pi is the full cycle time period, 0 to 2 pi phi m sin omega t whole square d omega t. Now here sin square phi m square by 2 pi sin square t equals to 1 minus cos 2t divided by t. So now here if you integrate this one, so if you simplify this one, the RMS value equals to phi m by root 2. Now here you can write the RMS value. RMS value is phi m by root 2 phi m by root 2 divided by, this is 2 phi m by pi. If you simplify this, you will get the 1.11. So this one, so this is important. This substituted, we substituted in the previous slide. So this is the 1.11. This one is the average and this is the RMS. And this one is a transformer primary winding induced EMF, transformer secondary winding induced EMF. Now, this is V1, N1, N2, E1, I1, V2, load, and I2. This is E2. This is a flux. Now, primary winding induced EMF, secondary winding induced EMF 4.44 phi m f into N1 and N2. Now here if you do the equation number 1 and 2, this is equation number 1 and this is equation number 2. 1 by 2, if you do that, E1 by E2 equals to 4.44 phi m f N1 divided by 4.44 phi m f N2. So this is same for equation 1 and equation number 2. You can cancel in the numerator and denominator this common term, this one. Now here E1 by E2 equals to N1 by N2. So this is known as the ratio of transformer primary induced EMF to the transformer secondary induced EMF, or transformer primary turns to the secondary turns is known as a turns ratio. This is most important, turns ratio. Now here turns ratio is different and transformation ratio is different. So that is E2 by E1, the ratio of secondary induced EMF to the primary induced EMF, that is E2 by E1. And next, transformer secondary winding turns to the primary turns, that is N2 by N1. And primary voltage and secondary voltage to the, this V2 divided by V1, E2 divided by E1, and N2 divided by N1, and this I1 divided by I2. So here voltage and currents are reciprocal. So here E2 by E1, N2 by N1, and V2 by V1. Here keep it in mind, this is I1 by I2. Remember this one, so don't forget about this, I1 by I2. So now here from these two equations we can say that transformation ratio equals to 1 by, transformation ratio is represented with capital K, and this one transformation ratio equals to 1 by turns ratio. The reciprocal of turns ratio equals to transformation ratio. Now this one. So if V2 is greater than V1, so if V2 is greater than V1, if it is greater than V1 and N2 is greater than V1, or K, this is the K is greater than K1, and then transformer works as a step up transformer. And if it is V2, next case, V1 is greater than V2, this one, and N1 is greater than V2 and K is less than V1. That is step down transformer, means primary winding turns are greater than N2. Primary winding turns are greater than secondary winding turn, that is step down transformer. So this voltage is greater than this voltage, then that is second step up transformer. So step up transformer and step down transformer. So this N1 equals to N2. Suppose is N1 equals to N2. What we call the transformer, that is 1:1 transformer. So if sometimes if these two turns are same. Now let us take one problem. It is desired to have a 1.43 milliwebers maximum core flux in the transformer at 110 volts. This is the V1 and 50 Hz. F equals to 50 Hz, and determine the required number of turns in the primary. Only one problem, and here E1 equals to 4.44 into F into 5M into N1. Here we have the flux value, that is 4.13 milliwebers, and here F equals 50 Hz, and E1 and V1 is same. So this is 110 volts. Now solution for this and the given data. Here F equals to 50 Hz and F5M equals to 4.13 milliwebers, that equals to 0.00413 webers. And next E1 equals to V1 equals to 110 volts. Now here this is the transformer, same thing. This is the formula, and N1 equals to E1 by 4.44 F into 5M. So this is the E1, this is the F, and this is the flux 5M. This flux is 5M, and this is the V1, this is the N1, and the supply frequency is 50 Hz. This you need to derive, you need to calculate. That value is 120 number of turns. And next, second problem. The EMF per turn, a single phase transformer, that is that transformer rating 2200 volts divided by 220 volts, 50 Hz single phase transformer is approximately 12 volts. Calculate the number of primary and secondary turns. The net cross-sectional area of core for maximum flux density of 1.5 Teslas. Tesla means Weber per meter square. Now here EMF per turn. EMF per turn means E1 by N1 equals to E2 by N2, that equals to 12. So we know this formula, E1 by E2 equals to E2 by N1 by N2. If you cross multiply, if you perform cross multiply for this equation, E1 by N1 equals to E2 by N1, that is 12 volts. Now here, so if you from this you can calculate the primary winding turns, and so here E1 is this one to this one is E1, and this is the E2. If you know the E1 and E2 and EMF per turn, then you can easily calculate the N1 by N1 and N2. So solution for this, the given data, E1 equals to 2200 volts and E2 equals to 220 volts. Now here F equals to E1 by N1 equals to E2 by N2 equals to 12 volts, and frequency equals to 50 Hz. So from this first calculate. So this is the transformer primary winding turns N1, N2, and this is the V1, this is the load voltage V2, E2 and E1. This is the current I1, I2 current, and this is the flux. Now here the formulas E1 by E2 equals, that is equals to 12. So 12 equals to, this is E1 and this is N1 and this is 12. So from this you can calculate the E1 equals to N1 equals to 184, this value. In the primary winding turns 184, and same way here N2 equals to 220 volts. This is 220 volts, and EMF per turn and E2 N2 equals to 18. This is step down transformer. Here N1 is greater than N2, 184 is greater than N1. Now here next to cross sectional area of the magnetic core. So cross sectional area of this magnetic core here. So maximum flux density of 1.5. We know this formula. E1 equals to this one. This one equals to E1 equals to 4.44 F into phi m into N1, and here phi equals to B by A. Sorry, flux density is given. Flux per unit area is known as the flux density, Weber per meter square. Now here B equals Weber per meter square. Here you can write flux equals to B into A. So now here this equals to B into A. Now here this is B into A. Now here N1 turns are 184 and frequency is 50 Hz and E1 is 2200 and B equals to Weber per meter square, 1.5 Tesla, and from this you can calculate the net cross sectional area of core, magnetic core, that equals to A equals to E1 4.44 F into B into N1, that equals to, this is E1 2200 and this is 4.44, this is the F, this is the B, and this one is the N1. If you take here E2 and you can take here N2, E1 and E2 you can replace with E2 and E1 and N1 you can replace with E2 and N2. Next, this value equals to this one. This is E2 and this is the N2. Now this value equals to 0.036 meter square. Cross sectional area of the magnetic core here 0.036 meter square. Now same problem, only numerical values change. EMF per turn of single phase 440 volts by 220 volts and 50 Hz transformer is approximately 15 volts. The number of primary turns and secondary turns. The cross sectional area of the core for magnetic flux density is 1 Weber per meter square. In the previous problem they have given in Tesla, and here B equals to 1 Tesla. Now here same procedure, second for solution for this one, E1 equals to 4.440 and E2 equals to 220 and F equals to 50 Hz and E1 by N1 equals to 15 volts equals to E2 by N2. Now here if you know the E1, then you can calculate the E1 N1 from the turns EMF per turn. So this one N1 and N2, this is the E1 and this is a E2. So the ratio of this EMF per turn is 15 and this is 440 volts, that is V1, and this voltage is 220 volts, that is V2. Now here flux density is 1. Now here this one EMF per turn, that equals 15, and this from this is E1, this is EMF per turn, and from this E1 equals to 29.34, that is 30 turns, approximately 30 turns. And next from E2 is 220 and N2 you can calculate if EMF per turn is 15 volts, that is 15 volts. So 15 turns, here 15 number of turns and here 30 number of turns. This is also step down transformer. Now here cross sectional area same, E1 equals to 4.44 F into phi m by phi m into N1. This phi m equals to B into A. this one B into A. Here you need to calculate this net cross-sectional area of the core for the maximum flux density. Now here E1 by 4.44 F into B into N1 equals to E1. Now here this is the E1 and this is the F and this is the B and this is the N1. F equals to 50 and flux density equals to 1 and N1 primary number of turns are 30 and E1 equals to 440 volts. And here this one, this is E2 and this is the F. To E2 equals to 220 and F equals 50 and this is the B and this is the N2 equals to 15. B equals to 1 Weber per meter square. Now if you calculate this one, that value equals to 0.066 meters square. Area units are, so this cross sectional area equals to 0.066 meter square. Now a 125 kVA transformer has primary voltage of 2000 volts at 60 Hz. So primary turns are 182 and secondary turns are 40. So this is N1 and this is N2, this is V1 and F equals to 50 Hz. Neglecting the losses and first determine the flux in the core phi m. No load secondary EMF, that is E2. So first solution for this, the given data, N1 equals to 182 and N2 equals to 40 and here V1 equals to 2000 and from this you can calculate V2, that means E2 also, and F equals to 50 Hz. So first write down this one. So this is the supply voltage V1 that equals to 2000 volts and N1, N2 is 40 and this is 182 turns and next this frequency equals to 60 Hz. Now calculate this flux value and this secondary induced EMF E2 value. So now here E1 equals to 4.44 F into phi m into N1, this one, and from this phi m equals to E1 by 4.44 F into N1 and this one, this is E1, this one, and this is 60, this supply frequency and primary winding turns 182. So now here the flux value is 0.041 Webers. And second one, number of turns, E1 by E2 equals to N1 by, this is turns ratio. Turns ratio, E1 by E2 equals N1 by E2. This is 182, substitute here, 182 and this is 40 and this is 2000. If you perform the cross multiplication for this equation, so 2000 into 40 divided by 182 is equals to E2. And now here E2 equals to 439.56 volts. So this is 439.56 volts. Now next question. A 250 kVA, 11,000 and 415 volts, 50 Hz single phase transformer has 80 turns on secondary. Calculate the approximate number of primary turns and maximum value of flux. First write the given data. Here E1 equals to 11,000 and E2 equals to 415 volts and N1 equals to 80. Sorry, N2 equals to 80 and calculate the N1. So E1 by N1 equals to E2 by N2. From that formula you can calculate the primary number of turns And same thing, flux formula in the previous problem. So this is the N1 and N2. So N2 equals to 80 and this is 11,000 volts, 11 kilovolts, and this is the 415 volts. And next, this is 50 hertz supply AC. From this, calculate the N1 primary winding turns and this phi maximum value of flux. So now there are formulas here. This equals to 11,000 divided by 415. This one, and this N1 you calculate, and N2 is 80. So if you cross multiply here, E1 into N1 into equals to, this is the E1 and this 11,000, and N2 and this one E2, that N1 equals to 2120. Here 80 number of turns only. Now here this is step down transformer. And next, maximum value of flux phi m equals to E1 by 4.44 F into N1. We know this E1, F and N1. Then E1 is this one 11,000 and F is 50 and this N1 is 2120. Now here the maximum value of flux is 0.0233 Webers. And next, a single phase transformer 400 primary turns and 1000 secondary number of turns. The net cross-sectional area of the core is 60 centimeter square. The supply voltage is 50 volts and the 50 hertz supply. And calculate the peak value of flux density and the value. Next second question, the induced EMF in the secondary winding. Induced voltage, that means induced EMF in the secondary. The solution for this one. So first, this is the given data. Secondary winding turns N2 equals to 1000 and primary winding turns N1 equals to 400. N1 equals to. Now here this cross-sectional area equals to 60 centimeter square, that equals to 60 into 10 power minus 4 meter square. Now from this, maximum value of flux density equals to, here maximum, this supply frequency equals to 50 volts 50 hertz. Now here phi m equals E1 by 4.44 F1. So E1, this one N1 and supply frequency. From this you can calculate the maximum value of flux value. Phi m 500, this one and this one. This is E1. First calculate the flux density, means B equals to 5 by A. So if you first calculate the flux value, then if you know this cross-sectional area, then you can calculate the flux density value. So here flux value, this is F and this is the primary turns and this value equals to 5.33 milliwebers. That flux density here, not maximum value of flux. Peak value of flux phi m by flux per unit area, that equals to 0.0533 Webers divided by 0.00, another 0 is a 60 and 0.006 meter square. Though this one equals to 0.93 Weber per meter square, that means Tesla. Now voltage induced in the secondary winding, same E1 by E2 equals to N1 by N2, that is turns ratio formula. So if you perform the cross multiplication for this equation, E1 N2 by N1 equals to E1. So this is the E1 500, this one, and N2 is this one, and N1 is this one 400. So secondary winding induced EMF equals to 1250 volts. Now next problem, a 15 kVA 2400 by 240 volts 60 Hz transformer has magnetic core of 50 square centimeter. So that means 50 square centimeter square means that is 50 into 10 power minus 4 meter square cross section and mean length of 6.66.7 centimeter and maximum flux density is 1.5 Tesla. Determine the number of turns in each winding and turns ratio. Here solution for this given data. So first this supply voltage is 2400. This is the 240 secondary voltage and this is 15 kVA. Next 660 Hz transformer. This area equals to 50 into 10 power minus 4 meter square and flux density equals to Bm equals to 1.5 Tesla. Now here the formulas related to this one. So total number of turns E1 equals 4.44 F into 5M into N1. So this 5M equals to B into A. This one, this is 5M. And here this one equals N1 equals to primary each winding turns E1 by 4.44 into F into B by A. This E1 equals to 2400. This is E1 and 4.4. This is the F and this 15 into 15 1.5 B value. This one and 50 into 10 power minus 4 this one. So now the value is 1201 number of turns in the primary winding. Same way here secondary winding, change this N1 and N2. N1 E2 value E1 and E2, so that equals to 120 number of turns in the secondary winding. Now the turns ratio equals to N1 by N2, N2 by N1. 120 by 1201, that equals to 0.1. So this is N1 and this is N2. 1201 by this one, this value equals to approximately 10 volts. 10 only. There is no units per turns ratio. I hope all these things are clear to you. If you still have any doubts in this lecture, you can comment in the comment section below. I will answer to your queries. Thank you very much to you all.
Like, share and subscribe. Hit the bell icon for more updates.